Hello everyone, welcome to our GasNZ Lunch and Learn webinar today. Great, we've had so many people who's responded to say they want this to attend this seminar. It's great to see you all. I'm Jeffrey Clark, Chief Executive of GasNZ, and today the topic is going to be Anaerobic Digestion 101. And to talk on that subject, we have Elsbeta from EcoGas. Elsbeta is the Chief Technical Officer who was instrumental in getting the country's first anaerobic digestion plant producing biomethane for the country's gas supply up and running. And she's going to give us a 101 on anaerobic digestion. In terms of process today, we're going to have an opportunity for a bit more interaction this time. By default, your cameras and microphones are disabled. You can use the Q&A button to post a question at any time. We'll see those and we can answer them after the presentation. We're also going to have the opportunity today to take live questions from people. If you want to raise a hand when we're taking questions, and we'll enable your microphone and camera to let you to respond to it. So without any further ado, I'd like to invite Elsbeta Boscova-Horton from EcoGas to talk to us about anaerobic digestion. Welcome, take it away.
Thank you, Jeffrey, and thank you all for making space in your day for learning about anaerobic digestion. It's my favorite topic, obviously. So yeah, but yeah, I really appreciate you guys taking time, and it was great to see the names and the organizations you represent. Just gives me a sense of satisfaction that we are all interested and keen to make biogas more prominent in New Zealand. And today we're going to talk about why that's important, but also how we can do it. So I'll start with a shameless pitch for EcoGas. So I obviously represent EcoGas, and EcoGas is a partnership between two companies, EcoStock and Pani Energy. And the reason why I speak about it here is that later on in the presentation we'll talk about what makes a good anaerobic digestion project, and that will explain why these two companies were perhaps more successful than others in establishing the first AD plant in New Zealand. So EcoStock has been in the business of collecting commercial food waste and turning it into stock feed for the last probably 15 or 18 years. And they are a privately owned business by Andrew Fisher, and Andrew is quite a visionary in the waste sector. And so if you haven't met him yet, he's a very interesting person and just incredibly enthusiastic and very sharp mind. And but so EcoStock was converting commercial waste into stock feed, but anything that contains animal protein cannot be fed to cows. So he was looking for a sustainable solution, because that portion of that food waste was always going to landfill. And that's how he came up with anaerobic digestion. And then he partnered with Pani Energy, and Pani Energy is owned by Central Lakes Trust down in Central Otago. And they're in the business of owning and operating renewable energy generation facilities. So wind and hydro stations, and they were looking to diversify, and together they created this limited partnership of EcoGas, and brought very complementary skills. So EcoStock knows all about food waste, where to find it and how to get it to the right places, and Pioneer knows all about running assets and looking after assets and generating energy and selling the energy into the market. So what actually is anaerobic digestion? Anaerobic digestion is a very ancient process, and it's very similar to what's happening in cow stomachs, but essentially it takes organic waste, food waste, and a rule of thumb here is kind of anything that you would feed to an animal or a human. So that excludes wood. So not many animals actually eat wood. So anything green or that has been produced by animals or grown essentially, and that's put through this process of anaerobic digestion. That's a biochemical process, and the process is very clever because it is able to convert 95% of the latent energy in that food into biogas, and essentially retain everything, all the good stuff, the nutrients and the trace elements that the food contains, is converted into a liquid fertilizer. So an extremely extremely efficient process, and the biogas it's a very flexible fuel and can be used in multiple ways. Upgraded to transport fuel or electricity, or directly used to process to generate heat. And bio CO2 or renewable CO2 is also a byproduct of the generation, or of the digestion, and can be used as well to replace fossil derived products. So what anaerobic digestion essentially does is it really shifts the dial from our BAU process, which is essentially landfilling. When food waste goes to landfill, it produces greenhouse gas emissions, converts into methane with a similar type of bacteria as the anaerobic digestion. But because landfills are open until they are finished and you can cover them, they are open, so all of this methane essentially percolates through the landfill and gets released into the environment. We have made some transition into composting. So composting sort of avoids the landfill emissions to an extent, and produces compost, which is obviously a valuable product. And where anaerobic digestion plays a good role is that it sort of shifts the dial even further into the avoidance space, because it produces liquid fertilizer and it produces biogas, which can then be used to replace fossil derived products and create that avoidance space. And one thing that is really fascinating about anaerobic digestion is that it sits at the intersection of 3 different sectors. So it's the environment, the energy sector, and then the agricultural, the primary production. And as fascinating as it is, it's also probably a weakness of the process, because not many people are able to actually, especially kind of regulators or policymakers, they usually play in their own sector, and it's very hard for people who set policies to step up and step out and really look at it holistically and say, right, we need renewable gas, but for that to be enabled, we need waste to produce the renewable gas from, and they have to cross the boundary of their own sector into the other sector. So it's all the anaerobic digestion professionals have always struggled with conveying the message, because people often look at it from one lens, and they miss out on the other attributes and the other benefits, which makes perhaps anaerobic digestion less attractive, unless you look at the whole spectrum. And so why does it matter? Why does anaerobic digestion matter in the New Zealand context? We've got some serious emission targets to meet, and we also have, and I've seen the lineup of people that were registering for this webinar. So I can't tell you. Sorry, I wouldn't be telling you how to suck eggs when you know that the natural gas stores are depleting, and we need a viable alternative. And also for our primary industries, we actually need to transition to a more circular and more lower carbon economy for our primary producers to remain relevant on the global market. And so these I see are the 3 key drivers for why I believe anaerobic digestion should be considered more seriously. And we've done some work with the Bioenergy Association to quantify what the potential is. And we believe that realistically there's a minimum of 20 petajoules of renewable gas that can be produced. We split it into 3 stages, and so with some serious actions from the 3 different sectors, and a little bit of a tailwind from the government behind us, I believe we can seriously achieve these targets. A little bit of a trip into the history. Not many people know that New Zealand was one of the first countries in the world that was producing or was converting biogas into vehicle fuel. Back in the 1960s and 70s, the government set up a research group down in Dunedin and Invermay that were tasked to convert agricultural waste into vehicle fuel. So they were running the first biogas upgrading machines and running tractors and vehicles on biogas essentially. So that's I find that a fascinating fact, especially when you then look at how the world has embraced this technology and run with it, whilst New Zealand kind of stayed behind or was left behind with all this amazing development early on. But what really drove the uptake of anaerobic digestion in the world were subsidies. And a lot of the countries recognize that in order to produce biogas or build that biogas market, they will have to incentivize the market through subsidies. And the biggest driver for biogas production in the world is the production of renewable energy. And whether it's renewable electricity or renewable gas, it's the energy aspect of it. And so a lot of countries put a lot of subsidies. UK, Germany, they put subsidies on the renewable energy produced from biogas plants, and that really drove the big growth of the sector. And the growth continues. And since the Ukraine-Russian conflict, a lot of the European countries have sort of supercharged the drive for the production of biomethane and injection of renewable gas into their networks to be able to seize the purchase of fossil gas from Russia. And so there's been a lot of investment and a lot of growth in the biomethane facilities. There's over 20,000 plants in Europe alone. So it's really a big growth. And the forward look still shows that there's going to be a 32% growth rate in the sort of immediate 5 years. And there's some really emerging markets at the moment. So India is chasing 5,000 plants by 2030, and Brazil is also looking to grow their biogas sector by 32% in the next 2 years. And interestingly enough, Brazil also does it without subsidies like New Zealand. So it goes to show that if there's a will, anything is possible. And I think we should embrace that as we move forward. So in simple terms, a business case for an anaerobic digestion project needs to have inputs, needs to have the technology in the middle, and then needs to know what to do with the outputs. And the success actually lies on the outside of the actual technology. The technology has been around for the best part of 40 years and has been commercialized and developed into a well-accepted and well-researched space. There's multiple suppliers that can supply the gear. So I think that piece in the middle, I would almost say it's the easiest part of the whole business case is the piece in the middle, the plant. What makes or breaks successful AD project is actually having a security of supply of the feedstock, and then having a security of offtake for the products that the system that the plant produces. And as we mentioned, there's the bioenergy sector, there's the energy sector, and then there's the fertilizer space as well. So in sort of globally, I spoke about the subsidies. A lot of the countries sort of put a lot of weight on the outputs, and that's how they drove the uptake of anaerobic digestion. We, on the other hand, New Zealand is the business case kind of stands and falls on the inputs and being able to charge gate fee for the inputs that are being processed in the plant. and that kind of builds probably 2/3 of the business case will be around the gate fees, and the energy will be in the last third. The energy and the fertilizer will be in the last third. And it actually shows or underpins why we haven't had anaerobic digestion plants built for the last, how many decades. It's essentially because the landfill disposal cost historically has been extremely cheap, and so it's only been since, in the last few years when the landfill levy has increased and landfill disposal cost has increased to a level where a medium-sized plant can compete with those gate fees. So at this stage, with landfill levy increasing, I dare to say that there's we finally reached the tipping point where business cases for anaerobic digestion plants can be built on gate fees lower than what landfills are charging for commercial food waste. Denmark had got it all right right from the beginning, so they're a bit of a unicorn in this whole space. They try to solve an looming environmental disaster with they've got a lot of pork and dairy industry agriculture, and because all of their animals are housed inside, they had a lot of manure to deal with, and so they saw that as a threat to the environment, and they decided that if they put the manure through an anaerobic digestion plant and create a biofertilizer from it, that's going to be a safer way of dealing with that waste. And then they sort of legislated that the digestate was going to be used as a primary fertilizer before any synthetic fertilizers are being touched. And with that, obviously, came the benefit of the biogas. So they were able to put subsidies on the energy production from those plants as well. So they seem to have got it really well balanced and put a lot of R&D behind it. And now they're enjoying massive production of biogas, and they're heading strongly towards having 100% renewable gas in their pipeline by, I think, 2037 or something like that. So actually, really just 10 years from now. So it's just to explain how the business case works for AD, and so I mentioned the global and the local drivers behind anaerobic digestion already, so I'll just quickly skip that one. But getting into the nitty-gritty of what anaerobic digestion is, a lot of people look at it and it's all tanks and steel and pipes, and you could look at it as a tractor, as a machine, but actually deep down inside those tanks, it's a living organism. It's I already made the connection with the digestion of cows. It's a very similar process, and you almost need to look after your AD plant the way you would be looking after a cow. So you need to feed it daily. You need to be conscious of what you are feeding into the cow, and you can't just turn it on and off. It just keeps going, and if you feed it too much, it bloats or foams. If you underfeed it, it eventually will die. And so it eats food and it makes gas and it also produces effluent. So I think that the parallel is actually very very matching in this case, and it kind of shapes the way we think about and how you need to think about what you would bring into your plant and as a feedstock and how you're going to deal with the products, obviously. It's a very powerful system. So the methane producing organisms are actually one of the oldest microorganisms on the planet at the moment. They've been around for millions of years, and they survived all the different eras, and that's actually explains why, or that's what has made them the way they are. They are very slow bacteria. They are very slow, and but they don't need much energy to sustain themselves. So there's that connection of they take 5% of the energy from the food that they process, and the rest is exerted as biogas. So they're very low energy needing, and they don't need much to sustain themselves, but they are very powerful in a way that they can process very concentrated waste and turn that into useful products. And the digestion is I'll keep carrying on with this parallel with the cows, but anaerobic digestion is essentially a 3-stage process which has to run in a complete symbiosis for the system to work. So the first step is hydrolysis, where the solid waste sort of breaks into liquid components, and in the next stage it's a acid formation where the liquid components get broken down into volatile acids or organic acids. And then in the third stage, the methanogens, they take the volatile acids and they turn them into biogas. And so it's kind of, and if you look at the cow, your mouth is the first part. When the food waste comes into the plant, you have to macerate it. You need to turn it into a slurry, so that what's happened in the cow's mouth, and then it goes into the rumen and goes into the stomach. And at the back end, you obviously get the gas, and you get the effluent. So really important to have, understand that it's a 3-stage process, but you need to keep that process in balance. And the way you do that is, I suppose we'll talk about it a little bit later. To give you a bit of a taste for what different feedstocks, how much energy they contain. Fats actually contain the most, or can produce the most amount of gas per ton of dry matter. So fats produce about 3 times as much gas as protein or carbohydrate, and then so residual fats, what you will get the most out of. There's a limit to how much fat you can feed into the system, a little bit like humans, but we'll touch on that a little bit later. And then food waste obviously has got a high gas yield as well, and then it sort of moves more towards the likes of the green waste, which has got a lower gas yield. And then what's actually almost surprising is that manure is actually has got a very low energy yield, because it's already been through one digestion system. So what the anaerobic digestion plants treating manure are doing is they're just trying to squeeze the last bit of biogas out of that already digested product. And but it's the sheer volume of manure that is being produced in the European countries that need to be processed, and that sheer volume still justifies being able to generate enough biogas to make a viable business case. So that's why there's a lot of anaerobic digestion plants treating manure in Europe. And it is actually all about the feedstock. It's about, because feedstock, what you feed, what your feedstock is made up of, influences how much biogas and how, what the quality of the biogas you produce, what the fertilizer is going to look like in terms of nutrients, and how efficient your system is going to be. So if you get your feedstock out of balance, you'll be struggling. The plant will be struggling. Also, the distance of the feedstock. Obviously, you've got the trucking cost as well to factor in, and it also defines, how much you need to pre-treat the waste. If you've got commercial waste, you have to depack it. If you've got energy crops, you have to store them for a big part of the year. So that kind of stuff is also determined. And last but not least, it actually determines how much you get charged for, how much you can charge for the gate fees, and how much you're going to have to dispose of at the end. So EcoGas, we've put this little graphic which kind of explains it in a graphic form. But what we are trying to say here is that all the fatty stuff produces a lot of biogas, and the meat and the milk drives the nitrogen in the liquid fertilizer. And this is how it's explained a little bit better. So we've got the 3-stage process, or it's drawn as a 4-stage process here. But the carbohydrates and fats, they are purely just energy. They are energy in a compact form, and the proteins is actually what has got the nutrients. So it's got the nitrogen, it's got the sulfur, it's got the phosphorus, and that's what influences the fertilizer. So you need to get a good balance of these 3 food groups, and to get your optimal outcome at the end. And I mentioned the fats. They yield a lot of gas, but there's a limit to how much you can feed into a digester, and it's basically driven by how much bacteria you actually have in your system. So it's a pure correlation of, you've got this much digestate in your tanks, and you can only feed this much fats. There's a level to which they can adapt, so you can run a keto diet or a very fatty diet, but you're sort of treading a bit of a fine line on the sort of inhibition, or where you get super high gas and where the inhibition starts. And it's a byproduct of the breakdown of the fats that actually inhibits the bacteria. It's a long chain fatty acid. And it's a little bit of sort of similar story with the nutrients and with the nitrogen. So protein breaks down and makes nitrogen or ammonia, and sulfur as hydrogen sulfide. And both of those, if they are in too high concentrations, they can also inhibit the bacteria. So again, you can't. It's hard to feed pure protein into a digester, and if you don't have means of reducing the ammonia and the hydrogen sulfide in the product, so you sort of stay below the limit. And so what's really the success behind a good digestion process is having the right amount of bugs for your feed. So we call it a food to microorganism ratio, or organic loading rate, and then having a really good mix, so the bugs have access to the feedstock. So in the digesters that we have in repertoire, mixing is one of the most critical things in the whole system, because you always have to make sure that your tanks are well heated and well mixed, so you don't have pockets of highly loaded bacteria where they are dying because they've been overwhelmed, and you've got half of the tank not doing anything. So mixing is one of the most important things in these anaerobic digestion plants. There's temperature plays a big role as well. So you can have most of the anaerobic digestion plants are running at mesophilic temperature, which is between 30 and 40. It's kind of the human body temperature of 37, 38 maybe. Or some plants also run at thermophilic temperatures, which is sort of the 55 degrees. It kind of makes more, in theory, it makes more gas, but it's also harder to control, because you have to be really, really onto it and maintain that 55 degrees, because if you allow the temperature to drop, your bugs will die. And so it takes a lot more logistics and admin to look after a thermophilic plant. If you can do it, it yields a little bit more gas than the mesophilic plant. And the pH of the optimum pH for digestion is somewhere between, it's around the neutral zone, so between the 6.5 and 8.5. And ideally, you will look after your bugs so you don't feed anything toxic. And so on the topic of toxicity, there's toxicity, which is that just kills the bacteria, and then there's inhibition. Inhibition is where they get sort of a bit flustered, and they don't operate to the best of their effects, best of their abilities. And the sort of the common sources of toxicity in digesters are cleaning chemicals. So especially if you are processing industrial waste or industrial byproducts, if there's a spill of cleaning chemicals, you could end up with inhibiting your bacteria or wiping out your digesters. Heavy metals, it's not so common in sort of food waste digesters, but it's very important to look at that for when like sewage sludges are being treated, because heavy metals could be quite high in sewage. And then we spoke about the ammonia and hydrogen sulfide. So these are the sort of the main groups of toxicants for anaerobic digestion. And just quickly touching on how would you know that your system is out of balance or is being inhibited. And there's this little trick where the methanogenic bacteria, although they're ancient and have survived a lot, they're the most sensitive of the three groups in this whole anaerobic digestion process. So if the system gets out of balance, you will know that because the methane producers will start sort of dropping out or being a bit behind. And this is where your volatile acids will accumulate and they'll start showing up in your system. So we use the volatile acids as our indicator of the system being out of balance. And I think I'm just about at the end, Jeffrey. I saw you coming in.
Yeah, we've got a couple of questions, so as long as we've got room for a couple more.
Couple more
So
slides, a couple more questions.
Yeah, why don't you finish off and we'll.
Yeah, just to give a bit of a tip of a hat to PERS 110. It's a standard that was developed in the UK that is kind of a guidance document on how to run an anaerobic digestion plant successfully, and it gives you a bit of a what do you need to look out for and what process you need to have in place so that your product is consistently good. It's got some plant design requirements, digestate sampling, and the Bioenergy Association is now working on essentially a New Zealand version of the PERS 110. But yeah, that was a bit of a race through the end, but hopefully I've covered everything.
Look, that was fantastic. That was a great overview of what anaerobic digestion is and how you guys are using it at EcoGas. And we've got a few questions through from people that I'd like to run through here. Two relatively easy ones. Can the sludge from a wastewater treatment plant be used to produce biogas?
Yes, absolutely. Yeah, it's probably the most common use of anaerobic digestion in New Zealand to date. So we've got a few wastewater treatment plants in the country that make biogas. So absolutely can.
Super. And more specifically for EcoGas, are there any future plans for another plant?
So we are in the process of building one in Christchurch and just getting through the resource consent stage right now, but design is underway, and hopefully we'll have a chance to do a third one in a short succession. But that's still sort of in development.
It's to get it to the resource consent process anywhere. And how long did it take from go to woe to actually get the Reparoa EcoGas facility up and running?
If I discount the COVID era, we essentially started building at the start of COVID. It's probably a year and a half of construction, and then a year before that of resource consenting and design. So on sort of similar terms. And Christchurch is very similar. It's taken us a year to get to close to the end with the resource consent, and it's probably going to take us a year and a bit to build it. So yeah, 2 to 2.5 years, depending on complexity of the plant or the speed of the resource consent process.
Yeah. And a slightly more political question. Last night on the radio, an organisation in Auckland was bitterly complaining about the cost per unit emissions of the green bins and lobbying strongly for the program to be discontinued. Do you have any comment on that?
Yeah, so the cost of the green bins, I think in Auckland, is about $1.60 per week or something like that. It's $70 per year. And I don't think it's all that much, to be honest. It's if that's all that we have to pay to have a better future for our kids and healthier planet, then I reckon that's money well spent. Yeah, that's my comment. Sorry, I won't dwell into it any further.
And perhaps just a final question. Someone's asking if you can give us a rundown of the Reparoa site's operation and has it been a success?
Oh yeah. Should we do it now or?
Yeah, I mean we've got probably a couple of minutes, and we need to wrap up so people can get back to life at 1 o'clock.
Yeah, I had it here, but I decided to get out of it. But do you think I'll be able to?
Somewhere in the 1,000 slides, the slide deck.
Yep, here we go. Can you see it?
Yep.
Yeah, so this is Reparoa, and I had a picture of this one. A bit of a schematic here. So Reparoa takes household, commercial, and industrial waste. Most of the waste goes through our consolidation facility in Auckland, where the little collection trucks unload, and we load onto line haul trucks and drive it down to Reparoa. Most of the industrial waste comes to us directly in tanker trucks, and we use the gas to produce electricity, and we've also partnered with First Gas or First Renewables on upgrading the rest of the gas, and that sends renewable gas into the pipeline, and renewable CO2 is going to go into the glasshouse. That piece is being commissioned as we speak. The fertilizer is spread by a local spreading company on the local farms, and used as a substitute to mineral fertilizers. This is our consolidation facility in Auckland. It's just a big shed with lots of bunkers where the trucks drive in and they unload, and we load it on the line haul trucks. It has to be super ventilated and odor managed because it's sitting in the middle of a light industrial zone. So we've got a monster of a scrubber there, and some extra features on minimizing the impact on our neighborhood. But Reparoa is so Reparoa, again, we've got a big shed in the middle, which is the only place where the food waste actually sees the daylight. This was where the trucks come in and they unload into this shed, and then the waste gets processed into a slurry, and that gets pumped into these digesters back here. These big bladders have now been replaced with the First Gas plant, and so I need to update my project. But line haul trucks back into the facility, they unload, and then we use the front end loader to feed this depacking system, which is essentially a hammer mill process that sort of rips open any packaging and by centrifugal forces separates light plastic and other packaging from the organic watery waste, and that gets processed into this slurry. It looks a bit like a smoothie, very green smoothie, and that goes into the digesters. Again, we've got a big monster of a scrubber to pull the air out of this processing hall and clean it before we discharge it into the environment. And then we've got digesters. The liquid product gets pasteurized before it goes onto land to keep it safe for the humans and the animals that meet with that product. And then gas gets scrubbed, and we've got a flare for disposal of any excess gas. And this is a picture of our CHP. So there was I actually do have the First Gas plant, but I think a lot of you know a lot more about it than I do. This is where we make biomethane, bio CO2, and you see the glass houses back here. So they'll be receiving the bio CO2. But that's a super exciting project for us.
Fantastic. Look, thank you so much, Elizabeth. That was really interesting. I actually learned quite a lot, even though I knew a bit about it already. So hopefully the participants who were here have enjoyed that as well. We'll be having more of these presentations as we go along, and there's hopefully quite a lot of exciting developments in the biogas and renewable gas space over the next year. So it really does feel like we're at a bit of a tipping point for getting traction on this. We know we've got the Minister of Energy interested in the topic. And several of us are working to increase that interest. So it does feel like an exciting time for renewable gas, and well done to you and EcoGas for what you've managed to achieve so far.
And thank you again for dialing in and wanting to learn. Appreciate it a lot.
Great. Thanks, everyone.
Have a great day.
We will have a recording of this available if anyone wants to check back on things later, and you can check in with us to find details of that. Thanks very much.
Thank you.
Bye.